In the last video, we introduced the idea of solving linear second-order differential equations with constant coefficients when we have the right side equal to a function of x. If you've not seen that video, please do check it. This video is just branching off from this, so I'm going to assume that you're fluent with that, or at least can appreciate it. The general solution of a differential equation in this form will give us y is equal to a complementary function plus a particular integral. The complementary function satisfies the differential equation here when this is equal to 0. The particular integral satisfies the differential equation in its entirety. So what we need to do then is first find the complementary function, and that is the case when d2y by dx squared plus 81y is equal to 0. Therefore we can use the auxiliary equation and say m squared plus 81 is going to be equal to 0. We can see this is going to have no real roots, and we're going to have purely imaginary roots. M is going to be equal to plus or minus 9i. When we have this form, we could now write that the complementary function, and we'll place it here, was going to be equal to a cos 9x plus b sine 9x. And if that means nothing to you, again, the previous videos have introduced this idea. So this is now a complementary function. We need to find the particular integral, and the particular integral is in the form k e to the 3x. So our trial function, what we'll have is the following. We've got it in the form k e to the 3x, so we will try it. Y is equal to p e to the 3x. The derivative with respect to x will simply be 3p e to the 3x, and taking the second derivative d2y by dx squared, we will now have 9p e to the 3x. This right here can now be subbed back through the differential equation to find our particular integral. The way I like to think about it, and again do check that this method is acceptable, we've got one of those and then we have 81 of those. Therefore what I can say now is 9p e to the x plus 81p e to the x is going to be equal now to the right hand side of the differential equation, 15e to the 3x. Okay, so now what we can do, what have we got? 9 and 81 is 90p, and that's going to be equal to 15. So therefore p will be equal to 15 over 90. 15 goes into 96 times. So p is equal to 1/6. Particular integral then is going to be equal to 1/6 e to the 3x. So general solution is the sum of the particular integral and the complementary function. So our general solution, y is equal to a cos 9x plus b sine 9x plus 1/6 e to the 3x, where a and b are arbitrary constants. So nice and sorted. There we go. All done. Let's have a look at another one. Okay, we need to solve this differential equation, give him a general solution. Again, we know that the general solution, when the right hand side is equal to a function of x, will give us y is equal to the complementary function plus a particular integral. The complementary function can be found by setting this to 0, and we would have, in this case, the auxiliary equation of m squared minus 2m plus 26 is equal to 0. That's not going to factor, so I'll complete the square. M minus 1 all squared minus 1 plus 26 is equal to 0. So what are we going to end up with? Plus 25. The roots should be 1 plus or minus square root of minus 25 will give us plus or minus 5i. Again, I'm assuming that you can spot the solutions to a quadratic that have complex roots. This now gives us the form that the complementary function can be written as e to the x, and then we're going to have a cos 5x plus b sine 5x. This is the type 3. So if you want a bit of a review on these, I think it's in the third video in the playlist. It's a type 3 case where we get e to the x, a cos 5x plus b sine 5x. Here is our complementary function. So if we were simply solving that where the right hand side was 0, we'd end up with that. We now need our particular integral, and this can be found in the form with we'll do the trial function of y is equal to pe to the x. The derivative with respect to x, dy by dx, is going to be equal to pe to the x, and the second derivative, d2y by dx squared, is going to be equal to pe to the x. I stressed in the last video that this lowercase p was not in essence anything to do with the capital P in the particular integral. I'm just using this for a constant. So what have we got here? We've got one of these, we've got minus 2 of those, and then we've got 26 of those. 26 plus 1 minus 2 is 25. So we've got 25 p e to the x is going to be equal now to 1 e to the x, which means now that 25p will be equal to 1 and p will be equal to 1 over 25. Therefore, our particular integral can be written in the form now of 1/25 e to the x. General solution, complementary function plus particular integral. Therefore, y is going to be equal to e to the x. Then we will have a cos 5x. In fact, let's just tidy it up. 5x, isn't it, in our complementary function? So a cos 5x. And then what we'll have now is plus b sine 5x. And then we will have plus the particular integral, which is going to be 1 over 25 e to the x. If you really wanted, you could factor this, taking e to the x out. So e to the x, and then we'd have a cos 5x plus b sine 5x plus 1/25. And that could be a solution for you. So a and b are arbitrary constants, and this is where we wind up. Please note that this video has been done as the extension of the last one. So if you're not happy with what you've looked at in the last one, or you've not watched it at all, and that has gone completely over your head, take a step back, have a look, and it should make some sense. So we've just solved linear second order differential equations where the right hand side of the equation is a function of x.